Welcome to ExplainerCast, episode 27. I'm your host, Dave Smith.
And this is Shane Swenson.
And we have some explaining to do. Today we're continuing our who knows how many part saga about the weather.
Yep.
This is part 2 of an unknown, to be disclosed number of parts about the weather. And today we are going to be explaining hurricanes.
Yeah, seems like if we started with lightning, one catastrophic release of energy, we should talk about another catastrophic accumulation and release of energy. So here we are.
Yes. The first one was electromagnetic energy. The second one will be mechanical energy.
Yep.
I guess.
Yes. Exactly.
Nice. All right. Hurricanes. I really only have an elementary school level understanding of hurricanes. And I just want to give you that understanding. And then I would love for you, Shane, to go super deep. But first, I want to say hurricanes every year remind me that there are extremely dangerous areas in the United States to live.
Mm-hmm.
And yet we still live there.
Yeah.
It's incredible.
They're really nice when they're not under the circumstances of a hurricane being right overhead. So they're also, I think, if you're thinking of like the nice, warm coastal cities
Yes.
along the Gulf Coast, I mean, it's a great place to be, except that that's also the perfect place for super strong storms. And so the rest of the time is great. But yeah, we'll talk a little bit about why are those areas the ones where these storms occur will hopefully be one of the outcomes from today's conversation.
These beautiful, tropical, warm water areas.
Yeah.
Let's just say when I was living in New England, Shane and I actually both lived in New England at different times.
Yep.
We never experienced a hurricane.
No. They did have something else though called a nor'easter, which could be pretty gnarly, but not, I mean, and definitely miserable. And I wouldn't want to be out in the water, but not as just severely destructive as hurricanes.
Yeah. All right. So, hurricanes. Shane, here, I'm going to give you my elementary school understanding.
Okay.
There's a few ingredients required for hurricanes.
Yep.
The first ingredient is warm ocean water.
Yes.
Like a gigantic body of warm water, and the only body big enough is the ocean. And I believe only on Earth, only the Atlantic Ocean generates hurricanes. Is that correct?
Well, that's by name. So these types of storms can occur in other places, including the Pacific, but they're often called typhoons when they happen in the Pacific.
Oh, yes. Okay, and is there any difference between them, between a typhoon and a hurricane, other than the location that they form?
I don't think so. We will see there's one difference that is determined by whether the storm occurs in the northern hemisphere or the southern hemisphere, but that's not really the distinction between a hurricane or a typhoon.
All right, so warm water, and it's crazy because I have no working intuition for why warm water would cause the air above that water to start spinning at 100 miles an hour and then go and destroy a bunch of beautiful hotels on the Florida coastline.
Yeah, it's not really obvious, is it?
No, I can't get from A to B on this one.
And again, this was part of what caused me to get curious about this a couple of years ago, because it's said so often that we take it as a matter of fact that these storms gather strength over water, warm water in particular, and then they lose strength over land. But similar to you, I didn't know why until I again went and looked it up. And so I'm going to share some of the information that I gained on that today.
Nice.
But you're right so far. It is definitely warm water that is a major contributor to the strength of these storms.
Well, we literally just hit the bottom of my understanding of the mechanism, so
Okay.
I think we need to hand it over to you. There are maybe one or two other fun facts that I know about hurricanes, but my intuition is just completely empty on these things.
Yeah, do you want to share those, or you want to wait till they come up?
Let's wait till they come up, but just a spoiler, one of them is the eye of the storm,
Yes.
which I think is a really cool fun fact.
Yeah, we'll definitely want to talk about that. Okay, so let's back up a little bit. When we're talking about storms like this is something that, of course, is unique to our particular climate and our particular Earth and its atmosphere and again, the oceans we have. And other planets that have atmospheres do also get storms. And those storms, again, are generated by the particular conditions on those planets. In a place that had no atmosphere, you wouldn't actually get storms, at least not this type, because these storms are fundamentally an atmospheric phenomenon. On Earth, I do think about the weather quite a bit. Again, partly I have a lot of hobbies that are weather dependent, and so that forces it.
Yes, you do.
And as we said last time, we all live our lives wandering around in this kind of this medium or this soup that is our atmosphere. and
Mm-hmm.
it's the air we breathe. It provides buoyancy for our balloons. It provides lift for our aircraft. It provides cooling and heating and even just the stabilization of temperature between night and day. It's obviously essential to life as we know it on Earth. And the weather is part of this. And without going too far into early principles before we get to storms, one of the key things that happens to weather on Earth is that the atmosphere is being heated and cooled in different places at different times.
Okay.
The sun shines on the Earth, and especially like dark, dry surfaces like rock heat up quite a bit. Surfaces like the ocean or water or lakes, they heat up much more slowly because they have maybe more heat capacity, or they can transfer that heat through circulation into cooler depths. Moist ground cover like plants and foliage will have water evaporating, which kind of keeps them cooler so they don't heat as fast. And then, of course, on the non-sunny side of the Earth, there's no direct heating coming from the sun. Things are cooling off, and different directions of exposure to the sun. So say like the sunny side of a hill or a mountain versus the shady side, get different amounts of heat applied to them. So if you looked at the whole Earth at any given time, you've got areas that are being warmed by the sun, areas that are cooling, and then other factors like clouds can actually reflect some heat back down to the Earth. They can also block sunlight. So just a very uneven heating of the Earth's surface is one of the key factors here.
Okay. And then is that relevant because when you have different temperatures of air, say a pocket of air that's hot next to a pocket of air that's cold, there's an equalization process that actually moves air between those two pockets.
Yeah, exactly. And so when you heat that warm air, it's actually going to increase in pressure, and then it's going to expand as a result. And when it expands, it actually is now lower density. And so it becomes buoyant relative to the cooler air around it, and it starts to lift. And I mentioned this last time when we talked about thermals, which you could think of as an unconfined hot air balloon, just this bubble of air that starts to lift up. And because it's surrounded by the rest of the atmosphere, other air around it is going to rush in to fill the gap or the void left behind by that rising warm air. And so that rising air leaves what's called a low pressure area behind it. And then air moves from a higher pressure area into that low pressure area. And when we live in North America, when you look at like the continental weather we experience, a lot of it can be explained by where right now are there areas of high pressure where the atmosphere essentially has more pressure in it versus low pressure areas where there aren't as many air molecules pushing out on the surrounding air. And as a result, the air is going to move from high pressure to low pressure. And so when you look at like a weather map and they have like an H on it or an L on it, those are showing you the centers of high and low pressure areas. And sometimes they'll draw like some blue or red lines with these little half circles or triangles on them that are showing these frontal boundaries kind of between the high and low pressure areas. And that's at a very macro scale. The air is sort of the atmosphere is trying to reestablish its equilibrium, but it's influenced by these uneven heating and then the uneven movement of air, that leaves behind low pressure and, creates high pressure areas as it moves. So all of this just kind of creates, I'll say, a breaking of uniformity or a breaking of symmetry.
Mm-hmm.
And that's the first part. The next thing that happens is if you have rising air and that becomes associated with a low pressure area, because as the air rises, again, it leaves less air near the surface behind it. So then that's a low pressure area. Air rushes in to fill it. And so in low pressure areas, which are associated with rising air, that air that's lifting up is expanding because it's under less pressure the higher it goes in the atmosphere.
Okay.
And so, at the limit, at the top of our atmosphere, there's essentially zero air pressure.
Uh-huh.
And actually what we experience at the surface, one way of thinking of it is it's the combined weight of all the air directly above you pushing down on you. And so the higher you go, there's less air above you pushing down, essentially. So the air will expand to fill the larger space as it goes up. And we experience this like, if you get a bag of chips, we live at a few thousand feet above sea level here. And like a bag of chips that at sea level might be kind of loosely packed but sealed, you bring it up here and it's now like tight like a Mylar balloon. And when you open it, like it pops open that, some of the gas escapes.
Totally.
And that's just because there's less air pressure right here at a higher elevation above sea level. And so that bundle, that pocket of air, as it's rising, it's expanding because it's not confined by some type of envelope, and it cools. And as we talked about last time, if there's moisture in that air, while it cools, it may in fact cross the critical threshold where it can no longer sustain all of that moisture in vapor or gas form, and that moisture then condenses into water droplets. And when it does that, it releases some heat, the heat associated with the phase change from gas phase to liquid phase of water. And that actually warms the air up, causing it to further increase in pressure, expand, become less dense, and then further lift higher into the atmosphere. So that happens, every day on an active day, where the sun's heating the ground, and this is causing rising air. We talked last time about how this can form thunderstorms, and these were when this cycle of rising air being heated through additional condensation of moisture in the cloud just becomes big enough that it's actually moving enough particles around to create an electric charge. And essentially, if you start with that idea and you do it at an even much larger scale, we'll see this starts to turn into what are called tropical storms, which then lead to hurricanes. And these storms, so often when I think about a storm forming, I think about it forming over land. But in this case now, we're going to add another component, which is what if the storm is actually forming over warm water? And so the key here is as the storm is growing and it's rising, it's causing air to rise and pulling more air into it from the side. If that air that's being pulled in is being pulled in across a warm body of water, the air that's coming into the storm from below is going to have a lot of moisture in it, high humidity, and it's going to stay relatively warm. If this were cold water, you might gain moisture as the air is pulled into the storm, but it's also going to be cold air, and it's going to take a lot of energy to heat that air up and make it want to lift up into the storm. But if that air is already relatively warm and the body of water kind of keeps it warm, even as it's evaporating water into that mass of air, you now get warm, high humidity air that's being drawn into the storm, where it then lifts up into the storm, condensing that water, which releases more heat into that mass of air, which causes it to lift higher.
Okay.
And if that air then sort of cycles back down at some point, or you just draw new air in, essentially bringing new warm water vapor into the storm and then releasing the energy of that water vapor when it condenses in the storm is how we're adding energy to the storm, as opposed to that terrestrial storm we talked about last time, where mainly the sun heating the Earth's surface is how we add energy. Here, that warm water vapor is actually the energy source carried into the storm and then released in the storm.
Oh, wow. So I've heard people refer to the ocean as a battery, and this would be an example of that.
Yeah, it's an analog of a battery. Like, it's not an electrical battery.
Right, but it stores energy.
That's right. It's a store of energy. And so, how that water get warm? Well, the sun has been heating it all summer. And in typical tropical storm season is in the late summer for a number of reasons, at least in the Atlantic, in specifically the Caribbean. And one of those reasons is that's when the water is nice and warm because it's had like a whole summer of heating. So yes, you've stored, day after day after day, you've stored energy from the sunlight in that body of water. And now the storm has given a mechanism to pull some of that energy together and concentrate it into a relatively small area and release it relatively rapidly, measured in days, as opposed to the weeks of summer where it accumulated.
Okay, so I want to ask a clarifying question here.
Yeah.
In the same way that we talked about clouds forming and generating electricity in the last episode, I'm hearing a lot of the same vectors directionally of the energy moving upward away from the Earth's surface up into the atmosphere and then cycling back downward in a loop, and then, of course, releasing heat when state transitions happen, and then, of course, just this accelerating system.
Yep.
But I'm imagining this motion along the z-axis, where the z-axis I'm visualizing as coming directly out of the ground and pointing straight up into the air. So this up and down motion. But hurricanes move in a circle around the z-axis, so like in the x and y plane.
Yep.
Right? So how do we translate? How does the motion translate from up and down to running in a circle on the XY plane?
Yeah, that's the key to what ends up leading to these really large storms that we call hurricanes. So let's talk a little bit about the vertical just for a second. So we pull moist air up into the storm, And at some point, even just holding that where it then condenses into water drops. And at some point, there may not be enough energy to continue to hold those water drops. So they may fall as rain. So, the water is being pulled in towards the center, lifted up, and then it may drop all the way back down as rain. Meanwhile, the air that comes up does eventually have to go somewhere. And typically, it sort of moves, once it's above the height of the storm, it'll move horizontally out away from the storm. And it's now relatively dry air because the moisture was condensed out of it and then fell as rain. And then that dry air can circulate and descend outside of the storm where it actually can then be recycled.
Mm-hmm.
So the air actually, where it picks up new water vapor moving across the surface of the warm water, picking up more energy. So there's actually this almost like conveyor belt of air coming into the center of the storm, lifting up, going out the top to the side, and then back down.
Okay.
And it's bringing that warm moisture into the center. So that's one way to think about sort of, okay, everything that goes somewhere, everything has to end up somewhere, and you can't just sort of concentrate a bunch of matter in one place and call it good. So that's the cycle of the airflow. And we talked about the movement of the heat and the moisture. So the next thing you ask then is, why does this become a rotating thing?
Mm-hmm.
In that plane or that perspective relative to the Earth's surface. And this is where the rotation of the Earth ends up being one of the key enablers of this type of storm.
Oh, I forgot that the Earth is rotating out from under this thing.
Exactly. And so there's this effect called the Coriolis effect. And you can experience this yourself if you can find a playground that still has a piece of equipment that you and I probably enjoyed as kids, but it's harder to find these days, called a merry-go-round, where you could spin this like flat platform as fast as you and your friends could get it going, and then see like who could hold on and who could get flung off. And
absolutely.
If you get on one of these, I've never tried this, but it would actually be really interesting to try to play like a game of catch with a ball with two people sitting on opposite sides of one of these. And the reason it's difficult is because even though you're facing each other, if you were to throw the ball directly at the person across from you, it's going to miss. By the time it gets to them, they will have moved.
They're gone. The ball's actually traveling in a straight line. It's not going to continue rotating because it's detached from the merry-go-round, right?
Yes. But there's two things. One, they move, which is a problem. But even if you were to try to throw the ball at the center of the merry-go-round, if you didn't correct your aim, you would miss every time, because when you throw the ball toward the center, the ball, even if you're aiming directly at the center, from your perspective, the ball has a component of its velocity to the side in the direction that you're rotating.
Right. The tangent line from where you are is its vector, right?
Exactly. The ball's going to miss to that side. And so this is actually what happens in a storm. The storm is pulling air in from all sides because it creates this low pressure due to the rising air within it. And we'll take the northern hemisphere perspective. If you were to look straight down at the Earth from a perspective above the North Pole, and I would just think of this as, okay, the sun rises in the east and sets in the west, so I am traveling on the Earth toward the east. And so if I'm looking at this from above, the Earth is going to look like it's rotating counterclockwise. And
okay,
as it's rotating counterclockwise, think of it like looking down at a merry-go-round that's rotating counterclockwise. And so
yes,
if something is moving north in the northern hemisphere, it's moving, say, from the equator or from mid-latitudes towards more northern latitudes. It's moving toward the center of that rotation, toward the center of the merry-go-round. And anything it's aiming for right now, as it moves further north, its horizontal component, which is to the east, is going to cause it to essentially miss, call it to the right. It's going to end up to the east of what it was aiming for if it's headed north.
Mm-hmm.
In the other direction, if you're heading from the center towards the edge, if you're heading south, like from a polar area towards a mid or lower latitude towards the equator, as you move south, the Earth that you're moving over is moving faster and faster to the east, and you're actually going to, again, now you're going to miss to the west. You're going to miss to the right again from the direction you were traveling. This result is that the air that's moving towards the center of the storm misses to the right.
Yes.
Whether it's going north, it misses to the right, which is to the east, or if it's coming south, it misses to the right. But it's still drawn towards the center by that low pressure. And so it tries to correct. It's always pulled toward the center, even as it missed to the right. And the result is the storm itself, the air that's coming into the storm begins to circulate in a counterclockwise rotation. in the northern hemisphere.
Okay.
And if you do this in the southern hemisphere, you have a low pressure system, which is drawing air in towards it. It's the opposite effect because now you have essentially a clockwise rotating surface if you look at it from the South Pole, and everything misses to the left, and you get clockwise rotating storms.
Okay. Does this same effect also explain why the total storm tends to move northward and westward
Oh, that's a good question.
in the northern hemisphere? Because don't they? Well, first of all, they always move westward, but that's just because the Earth is rotating out from under them, right?
Yeah, you get what are called trade winds, which are these specific kind of directions of wind, and you end up essentially at the very macro, because of this effect taking place, there are these kind of circulations that are always taking place. And the result is there are areas where there's like a westward trajectory, there's areas where there's an eastward trajectory. So I think those can definitely impact storms, especially ones at this scale. And an example we see that we experience is also something called the jet stream, which is this particular like high altitude west to east airflow in the northern hemisphere that I think is a result of sort of two different circulations where they come together, like one that's rotating clockwise, one that's rotating counterclockwise, and kind of between them then there's this like accelerated shot of air. I don't know that there's a specific east or west component as much as there are, depending on where you are in latitude, there tend to be prevailing winds that'll push you in that direction.
Okay.
So I think hurricanes can kind of track to the west, they can track back to the east.
Interesting. Okay. But the rotation is caused by this effect. And you said that's called the Coriolis effect? Is that what you said?
Yeah, the Coriolis effect. Yeah.
Okay. Oh, wow. I don't know how I got to this age without knowing that, but here we are.
And again, going back to like things you learned, maybe forgot or didn't care about, or at least for me, I can remember learning a weather unit, and we were told that low pressure systems in the northern hemisphere rotate counterclockwise and high pressure systems rotate clockwise. And a high pressure system is one where you have high air pressure, which is causing the air to actually spread out from that point. And so you get the opposite as it spreads away from a center. It actually will rotate. It'll kind of shift the direction it's going. And so high pressure systems rotate clockwise in the northern hemisphere, and then everything's inverted in the southern hemisphere. And at the time, I just was like, well, of course, I guess they do. But I never knew why. And it was never explained as far as I remember. But yeah, we live with this.
Mm-hmm. Very interesting. Okay. That makes a lot more sense to me now.
And I think this is one of the key factors as well, because this rotation then allows these storms to generate higher winds and kind of amplify all these factors, including the low pressure at their center, which is what's drawing all this air in the first place. And I haven't looked at this super carefully, but I think I've read that without that rotational effect, there just wouldn't be as much like total energy transfer, and the storms wouldn't gain nearly as much strength as they do when they're able to have this rotational component, which is a totally natural outcome of the Earth's rotation and its impact on the atmosphere.
So you're saying we could stop hurricanes from forming if we simply stopped the rotation of the Earth?
That's true.
Very, very straightforward.
I mean, it sounds like a good Superman solution, right? In fact, he could reverse a storm if he would just come and rotate us the other direction for a while.
Yeah.
I don't know what happened to, all of the other processes we depend on the planet, but
oh yeah, probably nothing bad. I'm sure it'd be fine.
no secondary effects on that one. Okay, so now we've talked a little bit about the energy transfer mechanism, which is we're pulling this moist air in, we're condensing the moisture to extract the heat from it, we're then discarding the moisture in the form of rain, and we've added that there's a rotation because as that moist air was pulled in towards center, due to the Coriolis effect, it actually missed and starts rotating around the center. And then this also leads to an acceleration of the winds and the destructive power of these storms, because as that rotating air is still drawn towards center by the low pressure at the center, it has angular momentum due to the rotation that's been induced. And as you pull a rotating mass closer to the center of rotation, it tries to maintain its angular momentum, which means it speeds up its rotation. It increases its velocity. And the classic example of this is like a figure skater when they're in a spin and their arms are out wide, their mass is far from rotational center. And as they pull their arms in, their spin accelerates faster and faster the tighter that they pull their arms in. And these storms essentially do the same thing. And so the winds near the center of the storm are the highest speed winds due to them having the smallest sort of axis of rotation, the smallest radius
Yeah.
that they're maintaining that angular momentum around.
Oh, that's interesting. So it's unlike a merry-go-round. The interior winds are actually moving faster than the outside winds.
Yes. Yeah, exactly.
In a merry-go-round, the interior, the further to the center you move, the slower you go.
Yep.
In linear distance terms.
Right. Yeah, and that's because the storm itself isn't a merry-go-round, but it's taking place on this giant merry-go-round, which is the Earth's surface, effectively, which is just there to give it that rotational kick, if you will. And then the storm builds its own rotational energy through the drawing in of that wind towards the center. So as you pull the air in, it's also lifting up. And again, that's due to there being low pressure near the center of the storm. It's due to the condensation of that moisture that was drawn in across the warm water and the release of heat associated with that. And I think the area of both highest wind and perhaps strongest updraft tend to be close to, but not exactly in the center of the storm. And you would think the very center would be the strongest here, but as the air is being drawn towards center and it's accelerating in its rotation, there comes this point where it's rotating so fast that to be pulled further into the center is fighting against that rotation. So think about the other aspect of this. When you're on that merry-go-round and it's spinning fast and you're hanging on to it, it feels like there's a force trying to rip you off of it. And
yes,
we call that centrifugal force because you feel it pulling you away from the center. The reality is that's a perceived force. It's not considered a true force by physicists, but it's really due to your frame of reference changing with the rotation of the merry-go-round. But nevertheless, it's like trying to pull you off the merry-go-round.
Mm-hmm.
And so these air and water particles that are being pulled by low pressure to the center of the storm as they rotate very rapidly, their momentum is essentially trying to pull them away from the center. And the point of equilibrium between those two effects forms what's called the eye wall of the storm, which is like this wall of clouds and high-speed winds surrounding the very center of the storm, which often is this clear, relatively calm area called the eye of the storm.
Okay. Talk about the wall. You're saying there's kind of a discrete wall, not so much a gradient to the center, but rather
it's a steep gradient.
You got
steep gradient that zoomed out. Like when you're looking at a satellite photo, you're like, there it is. I see there's this spiraling mass of cloud, and then I see this like clear cylindrical area in the center. I think there are multiple effects that contribute to this, but it's at least partly, I think, explained by the equilibrium between the centrifugal effect, the desire for all those particles to maintain their current direction of travel, which means they want to spread out from the center, versus the low pressure that's pulling them into the center. And they kind of get to where they're spinning so fast they can't come in any tighter than that.
Okay.
Another thing that takes place then is, well, what happens in the center? Nature abhors a vacuum. There's got to be something going on there.
Yeah.
And as a result, often in the very center, some of the air that's been lifted out the top of the storm actually starts to descend through the center. Most of the air goes outside of the storm and descends out past the perimeter of the storm, but some of it actually descends through the center. As it's descending through the center, it is warming up, it's increasing in pressure, and so any moisture that's still residing in that air evaporates, and that's why you tend to get this clear, cloudless area in the center of the storm. Not always, but it's common in the eye of the storm that there are no clouds. And this high-speed rotational kind of cylinder of air around the center, sort of, again, is going around it, and so often there are relatively light winds in the center as well. It's like relatively calm. It can be clear. Like if you're going through a hurricane and the eye passes right over, you get like the strongest possible winds as that edge of the eye, what's called the eye wall, passes over, and then it turns to calm. And if it's night, you'll see stars. If it's in daytime, you'll see the blue sky.
Oh my gosh. Can you imagine seeing stars in the middle of an eye of a hurricane? Oh.
And here's the problem. If you're in the eye, you got to get out because it means you've only experienced half the storm.
Right.
So then as it tracks across, eventually the other eye wall, the other side of the eye wall, the other side of this rotational cylinder hits you. The wind's going the exact opposite direction, and it's back at full strength, very rapidly. as the storm approached and you're out at the edge, it probably was building up sort of gradually and consistently. And then when you enter the eye, it sort of shuts down suddenly. And then when the other side of the eye comes through, it hits hard opposite direction, and you're
Yeah.
right back in it. And then, of course, eventually the storm moves on.
Oh, so do people report changing wind directions when the eye passes over
Yeah.
and then the other side comes in? It's like we were just getting hammered from one side, and now the other side of our house is getting. Oh man.
Yeah.
Wow.
And I like to think a lot of these things, like before, we have so much ability to observe things at macro scale now. Like we have airplanes and satellites, and we can see these things. But I try to think about what was it like when just here comes a storm, and it's one of the craziest, most intense storms you've ever experienced,
Yeah.
and then suddenly it goes like dead calm and quiet,
Yeah.
and you think, are we done? And then
Yeah.
the
Nope.
other side hits, and
Yeah.
you're like, oh
Now
no.
it's same intensity and the opposite direction.
Yeah. And it just defies all expectations of how nature works. Like things tend to happen in a consistent way. They tend to either be ramping up or ramping down. I don't know. I think it would have been, and you're probably just recovering from the terror of the first one and glad to still be alive. And then the second one hits. I can't even imagine the psychological pain that comes with that part.
Not to mention the physical pain.
And the physical. That's right.
I mean, getting hit with a barn door.
Yeah. That you had just thought like, oh, the wind's coming from that side. So I just had to put shelter on this side. And then suddenly, surprise, comes the other way.
It's in your back now.
Yeah.
We're in your base.
That's right. They all belong to us.
Oh my gosh. So fascinating. Are there accounts of people who have gone through the eye of the storm directly and come back to tell the tale?
The reality is like these are very destructive events, but if you're properly sheltered, you just hunker down and get through it. So yeah, people experience this with most significant hurricanes that make landfall. That the ones that have often the most destruction are the ones where the eye passed through and it has this ramp up, totally turned off and then back on behavior. But it's a relatively small area. Like, the storms can be easily, 100 miles across or more, whereas the eye might be 10, 20 miles across. So a relatively small fraction of the total storm, is going to have that, have that specific phenomenon associated with it.
Yeah.
Another thing I've read, so this sounds totally terrifying to me, but people that are in the wrong place at the wrong time end up going through hurricanes on boats. And
Oof.
yeah, I can't even, we didn't even talk about like what this does to the sea, to waves and things like that, not to mention just the sheer winds. But they'll talk about, in many cases, the eye is full of birds that got trapped and have just been like flying around trying to find a way out. But
wow,
they can't fly high enough to get over the top. Like these things can be, 10 plus miles tall.
Oh man.
And it's just out over the ocean, and the ocean's not exactly calm. Even though the air is calm in the eye, like the ocean's not necessarily calm because you've got all the storm waves that were generated by the surrounding storm. And so birds are just like desperate for a place to rest. And people have accounts of just like their boat being covered with exhausted birds when, their boat entered the eye of the storm.
Oh my gosh. Wow. Amazing. And how fast does the center of the eye of the storm move along the ground?
Yeah, it depends on the circumstances. I think of these storms as going in like the 1s to low 10s of miles per hour in terms of actual like motion. Even though the winds, I think a hurricane's defined as 70, 80 mile an hour winds or something like that, or higher. And the highest recorded winds are not quite 200 miles an hour, I think, like
oh my goodness,
170, 180, something like that. So
that's
these
so huge.
rotational winds are crazy fast, but the whole storm, macroscopically is moving at, I think, 1s to 10s of miles per hour.
So it is reasonable that a bird could stay in the eye of the storm and actually keep up with it. In fact, it would be slow compared to the bird's travel speed.
Yeah, it'd be just like, they're probably like flying around trying to find a way out. Like, is it over here? Nope. Over there.
And to them, it's just like, oh, there's way too much wind over there to fly in, so I'm just going to go back this other way. You know?
Yeah. Whatever their heuristic is for finding a safe place to land, it's not working.
But these storms last for days, right?
Yep.
Even before they make landfall. I mean, obviously, once they do make landfall, they diminish for reasons that I hope we've explained now.
Yeah.
But it could be 5 to 10 days in the ocean before it makes landfall, right?
Right. Yeah. And essentially, over that warm water, day and night, because the energy source is that stored heat in that warm water itself, these storms can build up, and depending on circumstances, they'll build up faster or more slowly. And so scientists will measure the speed of wind. The maximum wind speed is one way they talk about the magnitude of a hurricane. Another is they'll measure just how low the barometric pressure is in the center of the storm as another measure of its strength. And often, over the course of days, they start as like a mild storm to something more significant. Like they'll start with something called like a tropical depression, I think. So tropical meaning like part of the globe where it's taking place, in or near the tropics. Depression meaning it's a lower pressure area. And then if the water's warm and the circumstances are right for it to start spinning, like sometimes an injection of wind that kind of helps to start it up spinning will help get it accelerated. And now it starts to pull more air, moist air, and it starts to build strength. And then day by day, it can turn into a tropical storm and then to a hurricane. There basically are wind speed thresholds for each of those. So you're right. It could be that it was kind of not that big a deal 5 days ago, but for the last 3 days, it's been a hurricane. And
I see.
I guess if you're a bird flying in it, you're still looking for a place to rest.
That's like crazy. Can you imagine getting stuck? Okay, so when I hear the term tropical storm, historically I've just thought, oh, that's like rain in the ocean or in the tropics. But in reality, it's just really the difference between a hurricane and a tropical storm is just magnitude.
I think so.
They are the same shape of thing, just faster winds in the hurricane, right?
I think so. Yeah, I think it's just a scale that's kind of used with terminology to describe how fast the winds are, which is a proxy for how strong it is.
So here's a question you might not know the answer to, but during the daytime, the water is the warmest, of course, and I know, the sun, of course, it takes months to heat the water to its temperature that it achieves for ideal hurricane conditions. But at nighttime, when the sun goes down and the hurricane is still active above the water, does it reduce in intensity a little bit because the water is slightly cooler from the lack of sun?
So I don't formally know, but my intuition tells me that, if you turn the sun off for long enough, that might have an impact and diminish the strength of the storm. But I would guess that the change in surface temperature day to night in these warm water regions is small enough that these storms are able to gain strength to a certain extent, or at least maintain it overnight. It's actually an interesting question if there's a diurnal pattern of building strength during the day, losing strength at night. One thing to think about is the storm itself. Once it's kind of cloudy, it's actually covering, it's casting a lot of shade on the water surface where it is currently occupying. So that would probably diminish the day to night change in relative surface temperature below the storm itself.
Yeah.
And I assume that's the majority of where the moisture is coming from to feed the storm. So I guess I'll hazard that the sun was more important in preparing that warm water than it is in maintaining it, during the life cycle of the storm itself.
And of course, we know that in the tropics, the water temperature doesn't change much day to night.
Yeah.
Because again, the ocean is a gigantic store of energy.
Right.
And it takes a long time to cool it off.
Yeah. And this is part of what distinguishes this from terrestrial storms. Like terrestrial storms, like, again, right now, we're kind of going through some monsoon, we're actually coming out of some monsoon weather. Those very much have a diurnal component to them, which means during the day, the sun is heating the Earth's surface, causing fresh evaporation and lifting of air, creating storms that are going to build during the day, release their energy in the afternoon, evening, or nighttime hours, and then repeat the cycle again with the sun. And these water-based storms don't have as much of an effect, again, from the day and night transition.
Mm-hmm. Because the heat source is not only the sun.
That's right.
The sun does play a factor, I assume, right? But the water is maybe a bigger factor?
I think so. And probably even just in getting things started or kicked off. A lot of times, events like this need some relatively small input or stimulus to break the symmetry. And in fact, in weather, there's actually a study of weather where I think the term chaos theory first came into scientific usage as we know it now.
Mm-hmm.
And it was this phrase, a butterfly flapping its wings in the Brazilian rainforest, like leads to a hurricane or something like that.
Yeah.
And the idea is just that very small events can then cause some local phenomenon which can be amplified through a set of processes, eventually triggering a much larger phenomenon. And so it wouldn't surprise me to know that often like the sun heating an island or a particular landmass somewhere, kicked off a diurnal storm cycle, which then caused there to be a low pressure area, which then led to the formation of this storm, as an example. So I would definitely not discount the acute effect of the sun, especially in the initial conditions required for these big storms to form.
Yeah. So these are very moist storms. The air is saturated with water by definition. That's part of what causes them to happen.
Yep.
In our last episode, we talked about how moisture in the air dissipates electrical charge, which leads to less opportunity for charge to build up and lightning to form. Do hurricanes have lightning?
So I'm actually going to change what you said a little bit. We talked about how humid air seems to impede like static electricity charge buildup in our like human lives. Like we talked about, scrubbing your stocking foot feet on a carpet floor, and when there's more humidity, the static is reduced. But in storms, lightning formation itself is caused by the transport of charged particles from one place to another so they can build up a charge. And I think it's largely thought that the water in the storm is a key part of that transport, that the water drops or ice particles are actually moving that charge from one place to another.
Okay.
And yes, hurricanes have lots of that going on. And so they actually do, I believe, have significant thunderstorms associated with them. I don't know right up against the eye wall where the strongest winds are forming, but certainly in like the mid or more peripheral parts or the more outer areas of a hurricane are going to be kind of what seem like more conventional thunderstorms. They kind of come through in waves, and sometimes if you look at one of these storms on a satellite photo, you kind of see these spiral arms coming out of them. And those essentially are waves of thunderstorms, again, due to that moist air, being lifted up and causing that charge differential relative, either within the cloud or relative to the Earth's surface, resulting in lightning strikes.
Okay. Crazy. So let's just take the worst possible winds you can imagine.
Yep.
Combined usually with some rain.
Yep.
Then let's just add lightning to the mix. Why not?
Yeah, exactly. And the rain's probably torrential at times. The lightning probably seems excessive at times. If you're near the ocean, and you talked about these really nice places with nice, beachfront property, the sustained winds of these storms will push the ocean water like in sort of a large kind of massive, really long period wave called a storm surge. They'll actually push a bunch of water like up onto shore. So you're also going to get, sea-based flooding. But the only missing, like, super destructive things we have left are fire and earthquakes. And I'm sure those find a way to get involved from time to time, too.
Yeah.
Maybe asteroid strikes. Like, you could add those. But
yeah, exactly. Volcano eruptions.
Yeah, that's right.
Why not?
Yeah, sure. Do it all.
I don't know if you're going to know the answer to this question, but scientists have studied hurricanes in part by flying airplanes through them. Is that right?
Yes.
Is that actually possible?
It is. And yeah, I've read some of these accounts. I suspect like maybe they're not flying directly through the eye wall of the most extreme of these. Like flying through, almost 200-mile-an-hour winds seems pretty dicey. And I think these days they're more likely to send some drones through as well, flying drones. But yeah, there's this, they've had, like, I know that the U.S. National Weather Service has had programs to do this. I'm sure others have as well, where they'll outfit a relatively small plane with just a lot of measurement gear and some really brave or kind of, I don't know, like, yeah, we'll say brave or thrill-seeking kind of people, and be like, go fly into the center of this storm. And that means you're going through all the layers, as the winds increase. You're flying through thunderstorms, updrafts, downdrafts, rain, lightning, wind shear, turbulence. And then you punch into the eye of the storm, and you probably feel like one of those birds that doesn't want to leave. And then you got to turn around or find a way back out.
That's got to be a crazy transition into, I mean, I was thinking going into the eye of the storm, for somehow it just feels like, to me, that wouldn't be as crazy as transitioning out of the eye and back into the storm.
Yeah, I would think there's a little bit of that feeling of like, it's building incrementally as you move towards center. And I think there's a little bit of like, okay, we've gotten through everything up to this point. We can get through a little bit more, and you kind of just keep incrementally going for it. But once you're all the way inside, you have to commit to like the full experience immediately on your way back out. And I agree, that seems intimidating.
What's the diameter of a typical or diameter range of the eye of these storms?
I think it can range. So different storms will form different sized eyes, and I don't know all the reasons behind. Sometimes there almost isn't one, like it can be quite small, maybe a mile or two across. Sometimes it is covered with clouds, even though often they're clear. But I think more typically they're in the like 10 to 40 mile diameter
Wow,
range.
these are huge.
They're pretty good sized.
I mean, you mentioned that these things are crawling along at 10 miles an hour in some cases. So if you have a 10-mile diameter eye and your house is right in the path of the center of the eye, you could have an hour of calm between the front and back edge of the eye.
Right.
That's crazy long.
And again, yeah, I think it's hard to really comprehend just how big these are until you see them like overlaid on a map of the US, and they easily will cover, all of Florida.
Yeah, multiple Floridas in width usually, right?
Yeah, exactly. Sometimes it's a good chunk of the continental United States is essentially under, the perimeter of the storm. So they can be quite large, like, many hundreds of miles in diameter, from edge to edge. And so then the eye ends up being, large in, in terms of miles from our perspective, but relatively small in terms of the total scale of the storm.
Right, like single-digit percentage of the total diameter of the storm, probably, right?
Yep, and certainly of the area, yeah.
Yeah, for sure, even less percentage.
Yep.
Wow, amazing. Once again, we find that Earth, if you had a visitor from another planet who didn't have these things, and you explained what they are, they would probably ask why you live here.
Exactly, why you haven't left yet. Yeah, and there's this phenomenon where you just, as kids, I suspect we're just wired this way. Like, if we were shocked and surprised by everything novel, like, you wouldn't get through your day. So you internalize what normal is through experience, and then you look at it with perspective. It's like, what? This is nuts.
Yeah. Welcome to the hedonic treadmill. Just get back on.
That's right.
Hurricanes are normal.
Yeah. And you hinted about, just to be explicit, this question of, okay, why do storms lose energy or lose power? The wind speeds diminish when they make landfall. And I think there's really two reasons for that. One is we've taken away their key energy source, which is this inflow of moist air, because there's no just like free source of warm moisture anymore once they're on land. And then the second is, I think there's actually like a considerable amount of friction that the surface winds experience as they're moving over the terrain and the vegetation and everything on land. And so that tends to slow down the winds, and there's less energy coming in, to speed them back up. And so, as it turns out, as we were taught in school, we can these storms gain energy over warm water. They lose energy over land. And like sometimes, the trajectory will take them like across Florida and then back over water. And you'll see they like lost energy as they went over land, and they start to gain it when they gain back over warm water. If they head up into more of like the northern latitudes for, again, Atlantic hurricanes, as the water cools, then they gain energy more slowly. And again, if they couldn't sustain their peak winds, they'll start to diminish as well. There's still plenty of energy in those storms. They've got, big thunderstorms and so forth, but the maximum wind speeds tend to come down when they leave that sweet spot in the Atlantic.
Yeah. Okay, my last question for you. I hope it's okay to ask a final question. Do you have anything else?
No. Yeah, go for it.
We need to explain before I do that. Okay. This is going to be a completely speculative question, but let's go for it. Maybe it'll be fun.
Okay.
How big of an explosion would be required to disrupt the cycle of a hurricane and stop it in its tracks? Could humanity build such an explosion?
Yeah, could we nuke hurricanes?
Exactly. You knew where I was going.
Yeah. So how would this help? So I don't mean that to sound, maybe I do a little bit, but like, what part of the hurricane process would we be trying to disrupt with this big explosion?
Well, okay, it's a cycle, right? So water has a motion or water and heat and wind, they have this motion they need to follow. And if you stop that motion at some point, then there won't be more water on the heels of the water you stopped, water and heat and energy, to continue the cycle.
So yeah, if you could either stop the rotation, or you could reverse the low pressure center so that you weren't drawing air in. If you could do either of those things well enough, then yeah, you could turn one of these things off. I have no idea what it would take. I was thinking of similar questions though, which were like, if you had a way to measure, it actually would be interesting to ask, like, how could you measure the total energy in one of these storms? Maybe the total kinetic energy of all the wind, or the total potential energy of all of the elevated moisture, all the rain that's being held up by the uplift of these things, I wonder how much energy is actually there. Compare it to things we understand, like data centers or nuclear bombs.
Right.
They're just so big. My intuition is that they dwarf anything humans have ever built, but I don't actually know.
Yeah. I mean, the nuclear bomb option is not great because you would have to put so much nuclear fallout into the atmosphere to do that it would probably be worse than a
Some
hurricane.
side effects. Yeah. Let's say you get a super clean one that just like takes nice things that we are comfortable with, and
Yeah. It's a green nuke.
That's
Let's
right.
just call it that.
That's right.
I mean, the other option is you could put some kind of chiller lattice in the ocean water in the way of the path of the hurricane to cool that water down.
Yeah.
And then presumably it wouldn't have enough energy to pick up if it passed over the chilled water.
Yeah, I was reading. Oh, this was when I still hadn't graduated high school yet, but I remember reading an article where someone was trying to think about how to do that, and they'd come up with this device that essentially would cause like the top 100 feet of the ocean surface to kind of circulate, because you don't have to go down very deep till the water turns quite a bit cooler.
Yeah, good point.
And so if you could kind of like push the warm water down a bit and bring cool water up to replace it, you could meaningfully lower sea surface temperatures and essentially dramatically reduce the ability to form these big storms. Again, there were questions of over what scale would you have to do it? Like how much of the ocean do you have to cool by how much? And even how much energy does that actually represent in terms of stored energy? Again, the scale of these things is huge.
Right. And the answer to that question, the energy question, might be, well, you don't necessarily need to do it to all of the water in all of the path of the hurricane.
Mm-hmm.
And also, you might be able to reduce the temperature by just enough to weaken the hurricane, but not stop it. Like we don't mind the occasional rainstorm hitting the coast of Florida.
Right.
It's just when the winds are 200 miles an hour, that's a problem.
Yeah, exactly. And in fact, the reality is, storms are of all kinds of ecological benefit overall, but the super destructive ones are the ones we don't like. So yeah, maybe it's a little bit like wildfires and other things where in moderation, these things are great. And it's just in the extremity where they cause so much destruction that we dislike it.
Yep.
We'll see if that's a thing that future humans decide to
Yeah.
do. It's definitely it's probably becoming more technologically feasible all the time. And then there's the whole question of what are the side effects and should you actually do it?
Right. Should you do it? Right. Well, as engineers, we don't ever ask that question. We just build it.
That's right. Yeah. Unless someone says no. And who says no when it comes to the ocean?
Right. Who's there to say no?
Yeah.
All right. Well, thanks, Shane. We had some explaining to do. We did some explaining.
Indeed.
Is there any more explaining that's needs to be done here?
Not that comes to mind, Dave. So, yeah, hopefully we answered the questions.
Yes, I loved it. Thanks very much.
All right, you too.